Hello everyone. I'm going to go over a solution on how to balance a redox reaction using the half reaction method. And this question, we'll see that it's going to be in a basic medium, so I'll underline basic here to emphasize that. Our first step, I've already written out the instructions for the first step, and it's just we're going to balance everything that is not hydrogen or oxygen. So we're looking at sulfur and nickel. Those are the two non-oxygen, non-hydrogens, and we see that nickel is balanced on both sides, one on each, and sulfur is not. We have two sulfurs on the left, and we have one on the right. So to fix that, I'm going to put a coefficient of 2 in front of the SO3 minus 2. And I've left something out here on purpose to remind you, and this is a mistake that I can often make as well, or that I often see, is that we're simply, because there are several steps along the way in solving the solution or solving a problem like this, is that you forget to write the charges. So S2O3 has a -2 charge. So that seems to be the common mistake I wanted to highlight. All right, so next step then, because it really does affect the whole question, if you leave out your negative charges or your whatever charge you might have, is to balance, or rather to assign, oxidation numbers along the step of balancing this redox reaction. Okay, I'm going to rewrite this reaction without hopefully missing any of the charges. And I'll give myself a bit more room because I'm going to write above and below this reaction. Now, when you're doing this during a test, during a quiz, or even during your homework, you may not necessarily have to write out each of these steps, and it won't take you as long as this solution will, but I'm going through it for instructional purposes. Okay, so you're going to look for any existing charges. So if you have any existing ions, those are pretty simple. You just write, for example, this isn't the case now, but if you have, let's say, a copper ion like that, well, you know that the oxidation number is going to be 2+, so that you can just immediately solve. You don't have it in this case, looking throughout this reaction. So we're going to go ahead and first thing is then assign oxidation numbers to all of the oxygens. We know that they're always going to be -2. So throughout, we'll put -2. Then we look at the overall charge of each of these compounds, each of these substances, and we'll see that S2O3, their charges, their oxidation numbers for sulfur and oxygen should add to give us a -2. So if there are 3 oxygens, then each one has a -2 charge, so in total that gives us a -6. Now, you often don't have to show your work for this. This can be something you do on the side, or if you're comfortable enough, even in your head. But going through this now, we see that in total, oxygen contributes a -6 charge, which means sulfur in its totality. So both these sulfurs need to add to give us, together need to add to give us some positive value that makes the overall charge a -2. Now, that means it should be a +6. Now, hopefully that makes sense, because a +6, sorry, I hope I didn't say +6, I meant to say +4. +4 plus -6 will give us a -2. Right, now since there are 2 sulfurs, each one should have an equal portion of that +6, which means the oxidation number must be +2. Alright, so sulfur's oxidation number is +2, and oxygen, of course, is -2. Let's continue. Moving from left to right, we are at NiO2, and each of these oxygens again contributes -2 for a total contribution of -4. Notice there is no charge here. It's a 0 charge on NiO2. So nickel should balance out this -4 completely, and the only way to do that is to give it a +4 charge, so that is the oxidation number for nickel. Continuing left to right, we have a polyatomic here. We have hydroxide. Now hydroxide, just off to the side here, hydroxide has a -1 charge. Now we know that oxygen has to have a -2. Now for this to be the case, for the overall charge on this hydroxide to be -1, hydrogen has to therefore be a +1. So we'll say +1 here. Now we know that hydroxide has a -1 charge. To balance out the overall charge, seeing as there is no charge in nickel hydroxide, in nickel 2 hydroxide, without giving away the charge I just did, it has to be +2. Again, for each hydroxide, we have a -1 charge. So that means all of the hydroxide polyatomic here, each one is -1. Because there are 2 of them, it's -2. So to balance out the charge, nickel has to be +2. So it's nickel 2 hydroxide in this case. Okay, moving on to our last substance, we have 3 oxygens. Each one has a -2 charge for a total contribution of -6. Now it has to, SO3 needs to give us an overall charge of -2. Right, so for that to be the case, sulfur has to be a +4. Again, there is only one of them. I'm saying again because we saw something like this in the previous side, S2O3, right here, except here we had 2 sulfurs to contend with and to divide the charge, or the total positive contribution, and while here we only have 1. So all the sulfur, the 1 sulfur here can have a +4 charge. You don't take the coefficient into account here because each of the sulfites, SO3 -2, they each individually have a -2 charge. So we're looking at the oxidation numbers for just one SO3. So don't worry about the coefficients when you are balancing, or rather when you are assigning oxidation numbers. Right, so this is an important step because what we're going to do next is we're going to try to figure out how these oxidation numbers are changing so that we can then separate them into our half reactions. So and we see that S has changed. Sulfur's oxidation number has changed. It's gone from +2 to +4, right? So that's changed. So let's connect these. We'll talk about that in just a bit. The other thing that's changed is the other oxidation number that's changed is nitrogen. Sorry, I said nitrogen. I meant to say nickel. Nickel has gone from +4 here to +2. So that has changed as well. Okay, now let's analyze this. So sulfur has gone from a +2 to a +4. It has become more positive. That means it has lost electrons. So here we see it has lost electrons. We'll worry about how many it's lost in just a bit, but right now we can say it's lost electrons, and because it's lost electrons, it is an oxidation half reaction. And nickel, it has gone from a +4 to a +2. It has become less positive, which means in the world of electrons moving around that it has gained electrons. And if it's gained electrons, it's undergone a reduction reaction. Now you have to have both of these in a redox reaction, an oxidation reaction and a redox reaction. So it's good that we have that. We know that this will continue to work. Okay, now for our third step, let's separate these half reactions, and I'm just going to number them as 1 and 2. Again, this is where simple mistakes can happen. You forget to write a charge, so just be aware. Our second half reaction is going to be here. Okay, there we go. So we've written out these half reactions. Now for the longer step, because this has 2 parts to it, is we're going to balance now. It's hard to balance this. And first, we're going to balance our atoms, which include oxygen and hydrogen, and in that order. Then we're going to balance our charges. Okay, so let's do oxygen first. Okay, for our first reaction. So we're looking at the first reaction. I'm going to refer to this part up here. We have 3 oxygens on the left, and we have 6 because of the coefficient here. 2 and 2 times 3 is 6. We have 6 on the right. So we're going to add 3 waters. Because each water contributes 1 oxygen, you can add 3 waters into the left-hand side to balance out those oxygens. We'll count again after I finish writing this out. Okay, so now we have 3 oxygens here, 3 oxygens there for a total of 6. And on the right-hand side, we have a coefficient of 2 and 3 oxygens there for a total of 6. Now the oxygens are balanced. Now, just off to the right over here, I'm going to balance oxygens for our other half reaction. And in this case, I'm just going to rewrite it because as I write it, we can count the number of oxygens. There are 2 on the left-hand side, and on the right-hand side, there are also 2. So this is already balanced, and there is no need to balance oxygens on either side, or on this half reaction. Okay, so balancing oxygens is completed. We're now going to balance hydrogens. Okay, first reaction. Let's count. We have 6 here and none here. So we have 6 hydrogens on the left and 0 on the right. So that means to balance out the hydrogens, we're going to add hydrogen ions. And if there are 6 on the left and 0 on the right, we should add 6 to the right to balance it out. So it'll look like this. Right? Okay, so here are 6. Let me just fix that 6 there. Here are 6 on the right. Now we have 6 on the right and we have 6 on the left. Hydrogens are now balanced. Now our other half reaction, let's count how many hydrogens we have. We have 2 because of that subscript, right? We have 2 hydrogens on the right and we have none on the left. So to balance it out, we're going to write 2 hydrogens on the left. All right, so now the oxygen and hydrogens are all balanced, and we can continue by balancing our charges. Make that a 5th step, just to separate it. Okay, so I'm going to write these out. Again, you don't have to, when you are solving this yourself, doing your own work, you don't have to continue to rewrite these reactions. In fact, that's probably might potentially cause you to forget to write something, which is usually the mistake. So you can continue back and continue working on the solutions at this point here. I'm going to rewrite it just to show you that these are separate steps while we go through the solutions. Okay, so let's just rewrite this. Okay, before we add electrons, because this is how we balance charges, by adding electrons, let's just analyze this here. We have a no charge for water. See, there's no charge above water. We have a -2 charge for S2O3. Right, so overall, we have a -2 on the left-hand side, -2 charge. On the right-hand side, here we have something more to contend with. We have 2 different charges. So here we have 2 sulfites, SO3 minus 2. That means sulfite contributes a total of -2. Sorry, I said -2 and I wrote -4. It is -4, right? 2 times -2 is -4. Then we have 6, a positive 6 contribution from the 6 hydrogen. So in total, if we add these 2 numbers, add them together, we have a total contribution on the left-hand side of a positive 2. So these are the charges on either side, and we have to balance these. And the only way to balance this is to add electrons. So if both these sides have to match, and the only way to do that is by adding negative values, then we have to add 4 electrons on the right-hand side. Because positive 2 from here plus -4 is going to give us -2, which matches the left-hand side. So we've balanced charges by adding 4 electrons on the right. I'm going to just erase this work to give us some space. Okay, so Our first half reaction is balanced. We're going to continue now with our second. And let's just rewrite this. And again, you don't have to write all of these all over again. You can continue from the previous step where we balanced hydrogens. Okay, so going through this again, here we have a positive 2 contribution in total from the 2 positive hydrogens, 0 here from nickel 4 oxide, and also nothing on the right-hand side here. All right, so in total we have positive 2 plus 0. We have a positive 2 contribution on the left-hand side and a 0 on the right-hand side. So to balance this out by adding electrons, the only way to make both sides equal 0 is to put 2 electrons on the left. So 2 electrons we've now added to the left, and that has balanced our charges. I'm going to erase all this work. Balance our charges. They now both equal 0. No charge. Okay, we are almost done. Just a couple more things to do. Now, we have to balance. So we have to look at these 2 reactions here. And what we're doing in our 6th step is we're going to balance electrons between each half reaction. Because we see that here we have lost, right, in this oxidation reaction we have lost 4 electrons, and in the reduction reaction we have gained 2 electrons. So between these half reactions, the number of electrons lost and gained are not equal. So we need to find the lowest common multiple of electrons, and in this case that is going to be, well, I should add more to this. Well, I will say it is going to be 4. Okay, what we do though is you go to the highest lowest common multiple. So here we're going to multiply, because we're going to multiply by multiplier by coefficients. So to make the number of electrons lost and gained the same between the half reactions, we're going to multiply our second half reaction by 2. So I'll show you that step here. Our first half reaction, we're not going to do anything. We're just going to multiply that by 1, or nothing, just do nothing. I'm just going to rewrite this really. And don't forget your charges. Okay, our second half reaction, this is where we're going to multiply by 2, so that the number of electrons lost, 4, and are equal to the number of electrons gained. So multiplying each of these coefficients, so 2, 2, just a 1 over there and a 1 over here by 2 will give us this. Okay, now at the end of this step, you just want to make sure that the number of electrons lost, in this case 4, is equal to the number of electrons gained. If that's correct, then you have completed the step and you're now almost done. Let's see, have enough room here before I erase everything and make a new page. Just rewrite, add everything I see on the left on our reactant side, and add everything I see on the right on our product side, and then start canceling. So let's do that now. So 7th step, it's going to add and cancel. Now it'll look long and messy right now, but we'll clean it up at the end. Just enough room. Okay, let's look at both sides. So the first thing that should cancel out are the electrons, 4 on each side. Now we're looking throughout, and we also see, look, we have 4 hydrogens on the left, and we have 6 on the right, so all 4 are cancelled on the left, and we have 2 remaining on the right. Okay, and that seems to be everything we can do. Yep, there is no water. Usually you'll see waters will cancel out on either side. You'll have a certain amount left. In this case, that's not the case. So we are going to eliminate the 4 electrons, the 4 hydrogens on the left, and then 4 on the right as well. Electrons, 4 hydrogens on the right, except this time we're left with, in this example, we're left with 2 on the right. So let's start over. Well, not start over. Let's clear up this page. And I'll just rewrite the last line or continue from the last line. Let's see. You know what? I'll make a new page. Okay. So after we cancel everything out, and you can go back if you like in the video and see how that looked. But once we cancel everything out, which were the electrons and the hydrogens, what we're left with is this. Okay, and this is where you would stop if the question exists, or if the reaction existed in an acidic medium. But because the question originally said in a basic solution, we have one more step to do. So for every hydrogen ion, since this exists in a basic solution, we have hydroxide floating around, lots of hydroxide. So that is going to neutralize. It's going to neutralize the 2 hydrogen ions we see on the right. And if we are then going to add, for every hydrogen ion, this step here is going to add hydroxide ions for every hydrogen ion. What we then do to the right side, we have to do to the left as well. So we're going to add 2 hydroxides on the right, and that means we have to do the same thing for the left. So it'll look like this. Right, that's a new step here, or the new addition here, and everything else I'll leave the same for now. And this is where I've added the 2 OHs, which meant that I have to add 2 OH on the left. And I'm going to have to write this last part here just a little below, because there isn't room. Okay. Now, because I've added the 2 hydroxides together with the 2 hydrogen ions, these are going to make 2 water molecules. Now, I don't want to write the whole thing out again, neither do you, but you recognize that the 2 hydrogens plus the 2 OHs will make 2 water molecules. And what we did before in our last step is, before we got to here, is we added everything and we canceled. Now in this case, because we've added the OH on the right and created water, 2 waters, we can now cancel these 2 waters and reduce the number of waters on the left. So there were 3, since we've canceled 2, there's only 1 left. 1 H2O on the left. And we're finally done. Our final answer now is the simplified 2OH plus just the 1 water molecule, since we canceled 2 on either side. And you're done. This is the balanced redox reaction in a basic medium.